So now that we understand the structure of atoms and how valence electrons are kind of arranged and drawn, we're finally ready to start building up to molecules and compounds. And what molecules and compounds are, basically, it's where two or more atoms are connected by chemical bonds. There's some technical difference. Molecules consist of two nonmetals, while compounds consist of a metal and a nonmetal. But in biology, that's not all that urgent that we understand that difference. So molecules, compounds, slight difference, but kind of sort of similar. Anyway, so when we join these atoms together, we form a chemical bond. That is, there's a little joining structure, a bond, that takes this atom and this atom and sticks them together. And there's different types of bonds. So the first category of bond is called a covalent bond. It is a bond where atoms share electrons. Think co, like cooperate, share, and valence, electrons, covalent. So examples of where we see this: water is held together by covalent bonds, carbon dioxide is held together by covalent bonds, oxygen by covalent bonds. And then, in biology, we get into bigger molecules that are also held together by covalent bonds. DNA, glucose, phospholipid. I think DNA has this kind of mystical quality about it, but ultimately it follows the exact same rules we're talking about. It's got a bunch of atoms with valence electrons interacting through covalent bonds, and that's what gives it its structure. And we'll talk a lot more about that later in the course. So, so here's just some questions to kind of pause and reflect on. So I'd encourage you to pause. And did you pause and think? Okay, here's the answers. So electronegativity, remember, is the degree to which an atom attracts an electron. And when you based on which you know about electronegativity, which atoms will always share nicely. So do you think it's going to be the ones on the end, like the fluorines of the world, or is it going to be more of the ones in the middle? And hopefully you remember that fluorine is greedy and is not going to share very nicely. It really wants those electrons. And so it's not going to share very nicely. So the ones that share nicely are the ones more in the middle. Like carbon is a great share because, to get to that outermost energy level, it could either gain 4 electrons, 1, 2, 3, 4, or it could lose 4, 1, 2, 3, 4. So it could gain 4, lose 4, doesn't really care. Hydrogen, same deal. It could gain 1 and be full, or it could just lose the 1 electron it has and kind of be full. So these kind of atoms form nonpolar bonds. A nonpolar bond is a bond in which electrons are shared evenly. So there's kind of this equal sharing of electrons. So methane is an example of this. And, if you see carbon here with its 4 valence electrons, here's hydrogen. Each of the 4 hydrogen atoms has 1 valence electron. And so what happens is, since all of these atoms want to fill their outermost energy level, carbon needs to share with 4 partners to get to that full energy level. Each hydrogen atom needs to share with 1 to get to its full energy level. So this electron and this electron are shared to form this nonpolar covalent bond. These 2 electrons are shared to form this one, these 2 shared, etc. And you'll notice that now carbon has 8 electrons in its outermost energy level because it's sharing now, so that makes it happy and stable. Each hydrogen atom has 2, which is what it needs to be happy and stable. So by arranging themselves in this way and sharing these electrons, both carbon and the hydrogen atoms are able to satisfy that octet rule and become happy and stable, and that's why methane, CH4, exists. Unfortunately, not all atoms play quite so nicely. So a polar bond is one in which the electrons are shared unevenly. So here you have oxygen with its 6 valence electrons and hydrogen each with its 1, and they form just like before. But it turns out that oxygen is much more electronegative than hydrogen. Check out where oxygen is. It's right next to fluorine, that ultra greedy atom. And so oxygen is also pretty darn electronegative. And so it's going to tend to sort of hoard those electrons a little bit closer to its nucleus. Hydrogen, as we've seen, kind of neutral. It's like, I could take an electron, I could lose one, I don't care. And so it's not going to share those electrons quite as well, or hoard electrons at all, really. And so as a result, the electrons kind of get pulled towards oxygen. And that gives the oxygen atom kind of a slight negative charge and the hydrogen atom a slight positive charge. And that difference in charge means that these bonds are polar. The electrons are shared unevenly. And that has some pretty significant implications for water, which we will learn about in our next screencast. So covalent bonds, electrons are being shared. They could be nonpolar, where they're shared evenly, or polar, where they're shared unevenly. And by the way, you can think of the north and south pole, the polar opposites, right? So it's kind of an uneven sharing, opposite ends. Another category of chemical bond is an ionic bond. This is an attraction between oppositely charged ions. These form when one atom donates an electron to another because their differences in electronegativity is so great. So ionic bonds involve these things called ions. And an ion is simply a charged atom or molecule. So it's either gained an electron or lost an electron. So chlorine has a negative charge. Sodium has a positive charge. And take a moment to think, if chlorine is negative, does that mean, did it gain an electron or lose an electron? And hopefully you said gain, because electrons are negative. So if it's Cl minus, it must have one extra electron. So sodium has lost an electron. And then ions can be complicated things like this, CO3 2 minus. So this whole unit has 2 extra electrons. And so it's called a carbonate ion. And you probably remember working with these in chemistry. So how do these work? Well, let's go ahead and draw sodium chloride. So if you look at sodium, it's got 1 valence electron. Chlorine has 7 valence electrons. Make sure you understand why that is. So if we click here and draw that in, sodium has 1, and I'd encourage you to write this out. I normally do this on the board in class. So sodium has its 1, chlorine has its 7. Now, here's the deal. Chlorine is 1 electron away from being stable. It really wants 1 electron. It's very electronegative. Sodium has this extra one. If it can get rid of its extra electron, it's going to be back here and also be stable. So you've got one atom who's like, I really want an electron. You've got another atom who's like, I don't want this thing. So obviously it works out quite beautifully. Sodium's like, here, take my electron, chlorine. And when it does, it becomes positively charged because it's lost a negative. Chlorine becomes negatively charged because it's gained a negative. Both have satisfied the octet rule and they're happy. And then we call them ions because they're charged. But here's the thing, positive charges are attracted to negative charges. And so what happens is these are drawn together and they form an ionic bond. And an ionic bond is simply that attraction between that positive and negative ion. My charger's far away. We'll see how this goes. And so ionic compounds form these kind of crystalline structures as these negative charged chlorines and positively charged sodium sort of interact in such a way as to maximize the negative positive interactions. You can see this chlorine is surrounded by sodiums and each sodium is surrounded by chlorines. So this is why table salt is cube-like. It's because the little ions that make up that table salt are arranging themselves in this way to allow the positives and negatives to interact. Okay, so those were both bonds, both covalent and ionic bonds are between atoms kind of within the same molecule. Now we're going to look at what are called intermolecular forces. These are forces between 2 different molecules. So here's an example. Imagine you have HCl, which is hydrochloric acid. So chlorine is very electronegative, and so it has a slight negative charge, and we give it that little weird symbol there that says slight negative. Hydrogen, as we discovered, could take it or leave it, doesn't care. So its electron kind of gets hoarded by chlorine, so hydrogen stays as this partially positive charge. Well, if you put a bunch of these hydrogen chloride ions together, molecules together, the partial negative chlorine attract to the partial positive hydrogens. There's a little attraction here between these, and we call that an intermolecular force. This is in contrast to this bond right here. This is an intramolecular attraction. Within the molecule, this would be a polar covalent bond. Covalent because they're sharing, polar because it's uneven. There's a slight negative and a slight positive charge. A hydrogen bond is an example of an intermolecular force, and it's a weak interaction of a partially charged hydrogen with a partially charged negative atom. And they form when hydrogen is bonded to nitrogen, oxygen, or fluorine. And so here's some pictures, and I think it's worth drawing this out. So here's our water molecule. I said earlier that oxygen has a slight negative charge. That symbol wasn't on the screencast, but it should have been. So it has a slight negative charge. The hydrogen atoms have this slight positive charge. And so as water molecules come together, there's a slight negative here, a slight positive here. There's a little intermolecular force between them, and we call it a hydrogen bond because hydrogen is bonded to oxygen. And so that intermolecular force is there. Another intermolecular force is what's called a van der Waals interaction. This is a weak interaction between molecules caused by local charge fluctuations. So remember I said electrons are kind of arranged in these orbitals? I said it wasn't that important, but here I am bringing it up again. So, imagine that just randomly there's kind of electrons sort of moving around here, and then all of a sudden it just randomly kind of clusters. There's a slight negative end of the molecule and a slight positive, simply because the electrons kind of bunch up on one side just due to some random circumstance. Well, you can imagine if I bring a second molecule up to that one, since this is a positive charge, slight positive charge, that's going to sort of attract the electrons on this second, or the electrons on this second molecule. So these electrons kind of get pulled in, and that creates this little tiny weak attraction called a van der Waals interaction. Now, these are temporary. This isn't going to be permanent. They're temporary, and so eventually something's going to do something to these molecules, and all of a sudden that separation charge might go away, and then it's gone, but it'll reform again. And so these van der Waals interactions are extraordinarily weak, temporary interactions between different atoms, just caused by this kind of this localized fluctuation in those atoms. These are very weak forces, but they do become significant with really long polar molecules. And this is a molecule called a phospholipid that makes up a cell membrane. If you've had bio before, these probably look familiar to you. And so these van der Waals attractions become really important for these kinds of molecules. So that's it for molecules and compounds. We will wrap up chapter 2 with our next screencast, which is all about, what's it all about? It's about the properties of water.